So let me introduce you. So thank you everyone for joining us today. We have Cesar Ceballos talking to us about what is combinatorial reciprocity. But before we start, I would like to quickly mention our guiding principles. And once I find them here, they are that we're all learning and everyone has something to contribute and no one has all of the answers. And so if you have any questions today during today's talk, you can feel free to put them in the chat and one of us organizers will ask them for you, or you can unmute yourself and ask directly as well. So with that said, we're very happy to have Cesar Ceballos talking to us today. So please take it away.
Thank you very much for the nice introduction and for the invitation to speak here. I'm really happy to give this talk. When I was asked to give this talk, I was asked to give a talk which is kind of nice for a graduate combinatorics audience. So I decided to give a talk in a topic that is not completely related to my research, but it's a topic which I find really fascinating, and hopefully graduate students in combinatorics also find this interesting. Okay, so this is a topic where combinatorial reciprocities, and this was initiated by Stanley on a series of papers on the 70s, including one paper with the same name, combinatorial reciprocity theorems. And if at the end of the day you are interested in this, I really recommend Matthias Beck's and Raman Sayal's recent book from 2018, which is also called Combinatorial Reciprocity Theorems. Okay, so what is this all about? So in combinatorics, we often encounter problems where we are supposed to count something. And often counting these families of combinatorial objects, the solution is given by a polynomial. So by this, so solutions counting problems are often given by polynomials. So for example, we are counting a certain family of combinatorial objects, and the number of such combinatorial objects is given by a formula f of n, which is a polynomial. So this counts the number of blah 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 certain combinatorial objects, whatever thick paths, trees, whatever your favorite combinatorial object is, and this is often parameterized by some number. So let's say it's of size. And let's suppose Sarah is counting another family of combinatorial objects, and the solution is given by a polynomial g of n. This is counting another family of combinatorial objects. Well, it happens actually very often that when you evaluate one of these polynomials at negative numbers, so a priori this does not make any sense. So you are not counting objects of size -5. This does not make any sense. But often is the case that you can obtain the solution to one problem by evaluating another polynomial at negative numbers. So sometimes you have that you can get g of n by evaluating negative numbers, and maybe you have some negative signs there, so you take the absolute value. Okay, and this here is what is called a combinatorial reciprocity. This is called combinatorial reciprocity. Okay, and the purpose of my talk is to try to convince you that this is really interesting and this happens very often, and the problems that appear are quite interesting. So and I will do that by showing you some interesting examples. We start. We will see some interesting examples. Okay, are we good with this plan? Excellent. Okay, so the first one. So let's start warming up really slowly. So the first one is going to be about subsets and multi-subsets. Okay, so let me fix a natural number k. So let k in fix. So this is a constant number. And let me take a parameter n, which runs over the natural numbers. Okay. And the things that we want to count are really simple. So let me denote by C tilde of n. This is going to be defined as the number of subsets of size k of n. And this is, of course, very easy. This number C of n is given by n choose k. It's equal to n times n minus 1, and so on, to n minus k minus 1, so n minus k plus 1, divided by k. Okay? Okay, now let me ask you another question, which maybe is not that easy, but still doable. Now let me consider C of n the number of subsets or multi-subsets. Let me just write subsets of size of n. And now I will allow repetitions. Okay? So wait. And please feel free to interrupt me anytime. Okay. So let's say you need to pay a lot of attention in my talk. I usually like to make questions. So let's see, Matthias, what is this number? Give me a formula for this number.
Sorry, is that subsets of size k of and with possible repetitions?
So you have a set with n elements, one subset of numbers, and you allow repetition. So you can have something like 1, 1, 3, and 5. This will be a subset of 4. So you are allowed to repeat numbers.
Sorry, I'm freezing up. This is embarrassing.
Yeah, here, Matthias.
I think this is not easy, so it's not embarrassing. Anyone has an idea?
I think this is a balls and boxes problem. You've got your ones box, your twos box, your threes box, and your fours box. So this should be your n plus k minus 1 choose k.
Excellent. So what you're saying is you have n boxes.
Thanks, Mark.
And these are separated by n minus k, n minus 1 bars. These boxes are numbered from 1 up to n. And what you want to do is to start throwing balls in these boxes. And if you have 3 balls in box number 1, so you will get a 1, 1, 1. And then if you have 1 box in number 3, you will get a 3. So 1, 1, 3. Okay. So what you get is possible configurations of balls and bars, and you have k balls and minus 1 bars. So you have n minus 1 plus k choose k. plus k minus 1. Okay. And this is equal to n plus k minus 1 times and so on until times n divided by k factor. Okay. Now the magic comes into place. So first of all, notice that since k is a constant, this is a polynomial in n. So you can evaluate it at negative n. And if you evaluate the top one at negative n, so what you get here is minus n, then minus parentheses n plus 1, which is here, then n plus 2, minus parentheses n plus 2, which is here, and lately you get n plus k minus 1 with a negative sign. Okay, so you get exactly the second formula with a negative. Okay, so then we have that c of n is equal to minus 1 to the k c t of a. Okay, is this clear? Excellent. So this was my first example. Let's go to the second one. So let's change topics. Let's go to graph theory. So now let's consider proper colorings and acyclic orientations of graphs. The acyclic orientations. Okay. So let me start with a finite graph G. The finite graph. And chi G of n is chromatic. Okay. Does anyone remember what this is? So this one, chi G of n, is something defined as the number of proper n colorings. And what is a proper n coloring? So you have a graph, and now you are interested in assigning colors labeled from 1 up to n to the nodes in such a way that if you have two vertices that are adjacent, that are connected by an edge, then these two colors are different. So this means color vertices such that no adjacent vertices have the same color. Okay, so let's see how this is in an example. So let's do a very simple example. For example, let's take a triangle, and I want to compute the characteristic polynomial. So what I have to do is to color the vertices with the numbers from 1 up to n, and I want all of them to be different because they are all connected by an edge. So let's say for the first one, I have n possibilities. Now the second one cannot be equal to the first, so I have only n minus 1 possibilities. And the third one cannot be equal to the first or the second, so I have only n minus 2 possibilities. This is my polynomial. And now let's say that I'm interested in counting the number of acyclic orientations of this graph. So Sarah, how many acyclic orientations does this graph have?
It should be in factorial because if you have an acyclic orientation in this graph, you essentially have an ordering on the vertices.
That's right. So what's the number in this case?
3 factorial, so 6.
Okay, excellent. So acyclic orientations, number of acyclic orientations. In this case, it's 6. And now, since we are talking about combinatorial reciprocities, I want to evaluate this chromatic polynomial at negative numbers. So let's see what happens if I evaluate.
Before you do that, there's okay, never mind. Mark answered the question. There was a question about what is an acyclic orientation. But I think it's answered. Never mind.
Okay, so an acyclic orientation is so you orient all the edges of the graph either in one direction or the other in such a way that you do not form cycles in the graph. So in this case, you can orient each edge in 2 possible ways. So you have in total how many orientations? You have 2 times 2 times 2, so you have 8 possible orientations, and 2 of them will contain cycles. The one that is oriented in this direction of the edges, and the other one that is all the edges are oriented in the other direction. So in total, there are 6. Okay? Okay, now let's see what happens if I evaluate this chromatic polynomial at -1. So I get -1 times -2 times -3. This is equal to -6. And this is, of course, not a coincidence. This is here. That 6 times 8. A chromatic polynomial evaluated at -1 in absolute value is equal to the number of a cyclic. And here is a question for the ones of you who are very curious. A question: what is chi g minus counting? Okay. Excellent. Is this clear? Super. Okay, example number 3. Now let's change topic again and let's go to partial order sets. So let's go to posets. For posets, I will be talking about polynomials assigned to posets, and these are going to be ordered polynomials. Okay. So let's start with a poset. So let P be finite set. K elements. And let me define 2 polynomials. So the first one is going to be C tilde of n. This depends on P. And this is going to count the number of order preserving maps from P to n. So let me write this down. The number of, actually I'm going to count strict order preserving maps. Strict order preserving maps from P to, okay. So I want maps from P to n, so the numbers are from 1 up to n, that preserves order in a strict way.
If k equals n, question. If k equals n, is this the same as the number of linear extensions?
No.
Okay.
And let's be C P of n without tilde is the number of the same with the word without the word string. So what is an order preserving map? An order preserving map is a map from a poset, let's say to, in this case, to n, such way that if A is less than or equal to B in the poset, then the image of A is less than or equal to the image of B. And this is called strict if these inequalities are satisfied in a strict way. So that means if A is strictly less than B in the poset, then the image of A is strictly less than the image of B. Okay? Is this clear? Sarah, is this clear? Sorry, I'm always asking the same people because these are the first people in my screen. Okay, excellent. So let's do an example to one more. So example. So let's say P is equal to K. So these are the numbers from 1 up to K, order with the order of natural numbers. So this is just a chain. So K numbers like this. Okay. And now I want to compute this. So I want strict order preserving maps from the numbers from 1 up to K to the numbers from 1 up to N. So from each of these K numbers, I will assign a number, and these are strictly increasing. So what I count in is essentially K subsets of N. This is exactly what we did in the first example. So this is given by images. Is this clear? So again, I want to map these K numbers to the numbers from 1 up to N so that they are strictly increasing. So what I get is a subset, a K subset of N. So I just need to choose K. Now, similarly, without tilde, now I want order preserving maps. So not necessarily strict. So I'm allowed that two numbers are one less than the other, and the image has to be less than or equal. So the image of the first has to be less than or equal to the image of the second one. So you are allowed to have repetitions. So what I'm doing on this order preserving map from K to N, so I'm just choosing K numbers from this N chain, which are increasing, not in a strict way. So I'm allowed to have repetitions. So this is exactly what we did in the first example. So this is the answer to this number, or this counting problem is N plus K. So this is exactly what we did in the first example, and therefore it's a generalization. So let me do another example. So let's say P is, let me take, for example, this P. So this poset has 3 elements. And this one is less than this, and this one is less than this, and these are incomparable. Okay? So let me ask another person. Stefan, what is CP tilde of N?
So the baby is crying, I cannot.
I will ask someone else. Brandon?
I have a question, clarification. So is the strict order preserving map an if and only if statement? Or can two non-comparable objects be mapped?
If they are not comparable, there is no condition. They can map this way or that way, it doesn't matter.
Oh.
So let me do one, and you guys do let me do this one. So I want to assign numbers to these three nodes from 1 up to n in such a way that this number is less than or equal to that number, and this number is less than or equal to that number. That's all I want. So for example, if I assign here a number 1, how many possibilities do I have for these two nodes? So for this one, I have only 1 because it has to be less than or equal to 1, so it has to be 1. And for this one, it has to be 1 as well. So there is one possibility in that case. If this one here is 2, then this one here can be either 1 or 2, and this one here can be either 1 or 2. So I have 2 times 2 possibilities. This one is 3, I have 3 times 3 possibilities. So the answer is 1 squared plus 2 squares plus 3 squared plus n squared, and this is equal to n times n plus 1 times 2n n times n plus 1 times 2n plus 1 divided by 6. Okay. Now for the other one, it's similar, but now let's start the other way around. Now let's say, for example, if this one is n, then this guy has to be strictly less than n. So I only have n minus 1 possibilities. And the same for this node. So I have n minus 1 square possibilities. And so on. So I get 1 squared plus 2 squared plus n minus 1 square possibilities. And this is equal, if you just replace that formula, this is equal to n minus 1 times n times 2n minus 1 divided by 6. Okay. And magically, if you replace n by n minus 1 in one of these two equations, so let's say in the second one, you get exactly the first with a minus sign. So the proposition here is C E tilde of minus n is equal to minus 1 with C. Okay. So this is a generalization of the first example that I showed you before. Is this clear? Any questions?
Is it true for any graph or is it just for this particular graph?
It's true for any poset.
Okay, thanks.
Yeah.
Yeah, I don't know if I'd use the word, is this clear? I believe you. It's magic, but
It's not clear. It's magic. Okay, so let me erase a little bit the board and then I will go for the next example.
So how is this connected to Airheart theory? So if I plug in minus n, then I also get the integer points inside. So I have strict and not strict in Airheart theory.
That's my next example.
Okay.
But let me maybe answer your question quickly. If you want to relate that to Airheart theory, what you need to consider is a polytope and count integer points in polytopes And the polytope you use for this posets is the order polytope. And what you get is the same answer. Okay, so let me change topic again. Let me go to a more geometric topic, and this is counting integer lattice points in polygons. Or integer lattice points polygons. So this talk, let me just do an example in terms of polygons, like two-dimensional polygons, just very simple, plain polygons. Okay, so we have use of notation and we use P again. P, B, so let me P in R2, P a lattice polygon. So a polygon, any one of you knows what a polygon is. A lattice polygon is a polygon whose vertices have integer coordinates. This means vertices integer coordinates. Okay. And now let me define again two polynomials, and the goal will be that these two polynomials are related by a combinatorial reciprocity. So the first one is EHR P of n. This EHR is because of Airheart, as Stefan mentioned. And this is counting the number of integer lattice points inside the end dilation of this polygon. In other words, this counts the number of integer lattice points when I get by inside the polygon obtained by dilated by n the initial polygon. Okay. So this, and let me define Airheart P interior of n. So P interior is just you delete the boundary of the polygon, so you are not interested in counting points that are in the boundary, just only the interior ones. This is n interior. Here P interior is the interior. So let me do this with an example. This is much easier. So example. So let me draw a polygon. So this is my polygon. And let me just compute some numbers. So for example, what is Airheart P of 1? So again, the definition tells us you multiply your polygon. So this has integer coordinates, so multiplying by n, you just multiply the coordinates by n. So if n is 1, you just get the polygon itself. And you count the number of points, lattice points inside that polygon. So you just count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Airheart at the interior, evaluated at 1, is again you multiply your polygon by 1, so you get exactly the same picture. And then you count the number of points in the interior, so you don't care about the boundary. So how many of them are there? 1, 2, 3, 4, 5, 6. Okay. And it turns out, this is, I don't know if this is trivial for you, but this is not trivial for me. But Airheart, so in 62, that this is a polynomial. And this is not only for polygons, it's for polytopes in any dimension. And I did my homework and I did compute this polynomial for you. Let me write it down. In this case, is given by 9x squared plus 3n plus 1. And the interior, it turns out to be also a polynomial. So Airheart in interior of n is 9n squared minus 3n plus 1. And as you notice, if you evaluate the first one in minus n, you get the second one. And this is a result by McDonough from 71. This was conjectured by Airheart and then proved by McDonough. And this is, he proved that -1 to the dimension of P, the Airheart P evaluated at -n is exactly the Airheart of n. And this is a really, really beautiful result, which is known as the Airheart-McDonough reciprocity. Any questions? Okay, excellent. And many of these results, like for example, all the examples that I show you today, can be proved. Well, you can have combinatorial proofs which are rather involved but which are also really beautiful. But there are also really straightforward proofs using geometry, using this Airheart-McDonough reciprocity. So for example, for ordered polynomials, you just need to come up with a polytope, the ordered polytope, and then you just count integer points inside that ordered polytope, and then you get the result for free once you have these tools. So this is a really nice combination between combinatorics, numerical combinatorics, and let's say geometry combinatorics and the theory of polytopes. Okay. So I want to finish my talk with an open problem, which is an Airheart reciprocity conjecture, which I'm interested in. Okay. Five. This is an open problem by François Bergeron, which is, I won't mention anything about this topic, but this is related to something that is called multivariate diagonal harmonics, and it's connected to McDonough polynomials, representation theory, and many other subjects. But I will just try to put it like in laid down terms which are understandable to anyone. Okay. So 5, François Bergeron's Catalan reciprocity. Okay. Now for this conjecture, we will be working on a different topic. So we have seen graphs, posets, polytopes. Now let's go to polynomials. So let me consider polynomial ring. So let's Q x1. Let me write it like this: x, like rho x equal to x1 xn. Be the polynomial ring and variables. And when you are in this polynomial ring, you can consider a family of polynomials that are quite interesting, and these are called symmetric polynomials, or Sn invariant polynomials. These are defined as polynomials. So let's say, for example, x1 plus x2. These are polynomials that whenever you make a change of the labeling of the indices, then the polynomial remains the same. So if you change 1 by 2 in x1 plus x2, you get x2 plus x1, which is exactly the same. So these are called symmetric polynomials or Sn invariant polynomials. And now let me take I. This is going to be the ideal generated by Sn invariant polynomials with no constant term. And so here's an exercise for you. For exercise, this is not the conjecture yet. This is just an exercise. Show that if you take the quotient of this ring of polynomials by this idea, then the result is finite dimensional. And not only that, you can explicitly compute the dimensions. So the dimension of this Q x quotient by I is given by a really nice number. It's one of the nicest numbers in combinatorics. N factorial. Okay? And while you think about it, I will erase the board. Any questions?
It looks like there is a question in the chat, which is about why are you looking at Q instead of the real or complex numbers as the ground field?
You can also consider those rings. To be honest, I don't know if this makes any difference. I cannot answer that question at the moment. But something you can also do, which is really interesting, is you can also consider other reflection groups or complex reflection groups. And there is a vast amount of research in this direction as well. So this is interesting, for example, for Sarah, who is interested in this topic. Okay, any other question? Okay. Okay, so let's do not stop there. I consider a polynomial ring in n variables, but I can also consider the polynomial ring on two sets of variables. Say two sets of variables. I say Q of x1 n, y1 n. And now I also quotient by the idea of Sn invariant polynomials, and the Sn, the symmetric group acts on these polynomials the same way, changing indices in the x variables and changing the indices in the y variables. Okay? So if you interchange 1 and 2 here, you also interchange 1 and 2. And let me call this, let me write it like this. So Garcia and Heyman in 93 started computing the dimensions of these spaces. So it turns out to be also a finite dimensional space. And using computational computations, they realized that the dimension of these spaces is really nice. So dimension Q, and write both x, both y, I. This is equal to a really nice number in combinatorics, n plus 1 to the power n minus 1. And maybe some of you know this number. This is the number of parking functions. And this was conjectured by Garcia and Heyman in 93, actually earlier in 92. And this was proven by Heyman in 2002 using techniques from algebraic geometry. Okay. So this is not an exercise anymore. This is a little bit more complicated, but still quite interesting. But now that we have one set of variables, two sets of variables, why not to consider R sets of variables? Now, if you consider R sets of variables, you do exactly the same. You bring up polynomials and sets of variables. Symmetric group acts on these polynomials by changing the indices in each set at the same time. You quotient by the ideal, and then you get some finite dimensional space, and the dimension is a polynomial. So the Bergeron show let me just simplify this notation. Let me just call this dimension D. This depends on R, on N, and R. Is a polynomial in R for a fixed. Okay, so now I'm doing something completely different. So I'm not varying the number n. So I just let my n be fixed, and then I start growing the sets of variables. And then this happens to be a polynomial. And Bergeron's conjecture tells that if you evaluate this polynomial at a negative number, something really magical happens. So Bergeron's conjecture is the following. If you evaluate this polynomial at -2, you get Catalan numbers. So here, Cn minus 1 equal to Cn is equal to n, 1 divided by n plus 1, which is the n Catalan. And that's it. That's the conjecture. And with this conjecture, I finish my talk. Thank you very much.
All right, thank you. Let's thank the speaker. All right, so now we have some time for questions. There's one already in the chat. So does anything magical happen if you plug in -1 instead of -2?
And not that I know, no. At least not something to explain that easy.
Okay, any other
Also-
questions?
So when do we know a thing is like a when do we know that two counting polynomials or functions are reciprocals of each other? Do we have a sense of that? When do we know that two f and g satisfy this combinatorial reciprocity thing?
How do we know?
Yeah, so do we have any general ideas on when does this happen?
Well, I think
see
you
a
are
pattern.
probably two questions. So the first one is, so a combinatorial reciprocity is just evaluating a polynomial and negative numbers, you get the other one. This you
Yeah.
just can just test in a computer, and if it holds, then you make a conjecture, and that's the conjecture, maybe you prove it or you don't. The other question is whether you can approach this using, for example, a lattice enumeration of polytopes. So the question of whether you can, so if you have a combinatorial problem in your PhD research topic, and you have a counting problem and you have a polynomial, you can ask yourself, is this polynomial given by the Airheart polynomial of some polytope? And there are tools to approach that.
Right.
Yeah, so you have to compute certain things, H polynomials and things like that. And then this gives you some hints of whether there exists a polytope that you can use for your problem. So there are some techniques, but of course it doesn't give you the polytope right away. So you can prove things like, okay, there is no polytope that is giving you that polynomial, but it does not give you the polytope right away. So you need some ingenious idea to find the polytope.
I had a question to make sure I was understanding this DNR polynomial. And so I believe looking at this, so so DN1 is always in factorial and DN2 is always n+1 to the n-1. Am I interpreting what we have on the board correctly?
Almost. What you should do is D1R. Oh, no. Wait a second. Yeah, you're right. DN1 is n factorial. DN2 is n+1 to n-1.
Okay.
And this is kind of like if you look at, like, I don't know, people working on flow polytopes, there are some of you that are working on that, I think. There are some kind of similar results where you count like points in flow polytopes and something, you get parking functions, you get n factorial somewhere, you get also Catalan numbers. So you get kind of a feeling, oh, maybe there are some flow polytopes around there. I have no idea. Also, let me mention something that is also some of you might be interested in. So for example, there are some formulas for these polynomials DNR for small values of n, which can be explicitly found using the Nutamari lattices. And I think Matthias has worked on that. maybe there is also something there to be used. I don't know.
Question. So in the case of the Airheart polytope, the minus n actually has some sort of description, right? Because when you consider dilation, you can map a point to its, so you multiply all the coordinates by n. But in this case, you can also like multiply the coordinates by minus n, which makes sense.
Yes, but the solution is not the same, because when you multiply
Wait,
by minus n, you just get a kind of a, you get the same
you
polytope
like
in a
reflected.
the number of points is the same.
Hmm.
So it's not
Yeah, but
right.
it's not.
The intuition is right, but the result is not right. So you are not counting points in minus n times p. You are counting points in
Yeah.
the
Do you have some intuition for like where the conjecture is coming from, like where the Catalan numbers are coming from in this, or why they appear?
no.
That was really
But
nice, by the
I
way.
have I mean, I have thought about this, but nothing fruitful so far. But many good ideas, but nothing fruitful.
Thanks.
So I think you gave two exercises, as I recall in the talk. One was interpret the negative values of the chromatic polynomial past -1. And the other was this Bergeron, the understanding why the dimension of dn1 is n factorial.
Yes.
So I've read Stanley's original paper on the chromatic reciprocity theorem, and that feels like a generally tough construction to kind of do on your own. I know. I guess I'm asking, how long should these exercises take?
It depends. I think like in this, it may take really long.
Okay.
You have the right tools, it takes shorter.
Mm-hmm.
So for example, for the case of graphs, I mean, if you know the answer already,
I do.
what the chromatic polynomial evaluated at -n counts, then there are certain tools you can use for proving that. And these are very common in combinatorics. These are, for example, deletion, contraction arguments that are, for example, in Maythrow theory. And then you kind of can prove these kind of results. Maybe you need some time, but you can prove them. But you need the right tools. Like don't be, if you don't manage to do these problems, it doesn't mean that you are wrong on anything. These are like, you need the right ideas to be able to solve. Yeah. And for example, for the dimension, this is also not that simple. If you get some hints, maybe if for example, I mentioned, okay, look at the van der Monde determinant and all its partial derivatives, and this is counted by n factorial, then this can give you a hint of how you can prove this kind of result. But from scratch, these are difficult exercises.
There's one more question in the chat. Can Bergeron's conjecture be formulated in terms of Airheart theory on a polytope?
No. So that was my first attempt to find a polytope, like, I don't know, like flow polytopes or something. They need to, of course, to have the right dimension. But there is, so I know that there is no polytope whose integer lattice points are counted by these polynomials. But if you look at Stanley's approach to show this combinatorial reciprocity theorems, they do a lot of integer lattice point, like counting integer lattice points in, let's say, cones or polyhedral cones, simplicial cones, and there might be some things to do there that do not quite look like polytopes, but also have like some geometric flavor. But you need to come up with the right set of lattice points you want to count anyway. And this is, you need some divine inspiration.
Awesome. Well, let's thank Cesar one more time. That was excellent. Thank you.